In this video, I would like to present our recent work on one-way functions and zero knowledge. The question we consider in this work is this: how does one-wayness relate to knowledge in proofs? Our starting point is the knowledge proof systems from foundation of cryptography. Let's consider the following situation. There is a formula which represents some constraints for a social problem, and we do not know whether there exists some satisfying assignment for this problem. Now, some person came up with the solution, and he claims that there is a satisfying assignment for the given formula. And another person wants him to prove the existence. The trivial way is just to send the assignment itself, but this assignment can be very valuable knowledge. So this is a satisfying assignment for the social problem, so this person may want to do some kind of business by using this assignment. So the question is, can this person convince the other person without revealing anything other than the existence? This is the goal of the zero-knowledge proof systems. The work by Goldreich, Mikali, Wigderson yields an affirmative answer to this question. If there exists a one-way function, this is a function whose computation is easy, but inverting its average gets hard, then the answer is yes for every given NP statement. Now I explain zero-knowledge proofs more formally. Zero-knowledge proof is an interactive proof system with additional zero-knowledge properties. So now we consider a zero-knowledge proof for a promise problem pi. An interactive proof system for the problem pi is a pair of time-unbounded prover and efficient verifier. Both parties are given an instance X, and the verifier can also use the internal randomness, and this is secret to the prover. The task of prover is to convince the verifier that the given instance is actually yes instance, and he sends some message to the verifier. And depending on the message, the verifier replies something. And depending on this verifier's message, prover again resend some message, and they do interaction. After polynomially many steps, verifier determines whether the given proof interaction is acceptable or not. And this needs to have two requirements: completeness and soundness. The completeness says that if the given instance is actually yes instance, then the verifier can accept the proof with high probability. Let's say 1 minus negligible in this talk. The soundness says that if the given instance is no instance, then the prover's claim is false. And in this case, every inefficient prover cannot convince the verifier. So the verifier can reject the proof with high probability. And since the prover is time unbounded, this proof may contain some non-trivial knowledge of prover. The zero knowledge property asks to prevent such a leakage of additional knowledge. And this is discussed by the simulator paradigm, so the existence of simulator. This simulator is efficient algorithm, and it is given an instance X, and the task is to simulate the verifier's view on this interaction. Since this simulator do not have any interaction with this prover, this outcome does not contain any knowledge of prover. And if this is indistinguishable from the actual conversation, then particularly computationally indistinguishable, then we can regard that this does not also contain any knowledge of prover accessible by efficient adversaries. The zero knowledge property, actually computational zero knowledge property, is defined based on this idea. The statement is for every yes instance and for every efficient verifier, there exists a simulator such that the verifier's view is computationally indistinguishable from the outcome of this simulator. And this is the class CZK, which is a class of promise problems that has computational zero knowledge interactive proof system. And the previous work by Goldreich, Mikali, Wigderson proves that if there exists a one-way function secure against non-uniform adversaries, then every NP problem is contained in this class CZK. And the follow-up work also proved that if there exists one-way function, then we can also obtain another type of zero knowledge for every NP statement, SZKA, which stands for Statistical Zero Knowledge Argument System. And there are two differences. First, this is statistical zero knowledge. So zero knowledge property is stronger than the computational one. The simulator statistically simulates the verifier's view. And this is argument system where we consider a weaker soundness requirement, computational soundness, which means that soundness holds for every efficient provers. Both yet that NP admits computational zero knowledge argument system by definition. To sum up, if we have one-way function, then we can obtain biased zero knowledge for every NP statement. In this work, we consider the converse. Is one-wayness required to construct zero knowledge for every NP statement? When we consider this question, we need to be careful a bit because there is an interesting case. Let's consider the following situation. So we have an interactive proof for some promise problem. And if the verifier can solve the problem by itself, then there is no interaction between the prover and verifier. And this is trivially zero knowledge proof because there is no message from prover. So there is no leakage of the knowledge. Namely, if the problem is worst case easy, then we can obtain trivial zero knowledge proof regardless of the existence of one-way function. And this is not interesting at all because this is zero knowledge, but we also do not need the prover itself. So let's consider the non-trivial case. How about non-trivial worst case hard cases? In this case, we need the prover essentially because the verifier cannot solve the problem by itself. And so the zero knowledge property should be meaningful. And this is asked by Ostrowski and the follow-up work by Ostrowski and Wigderson. And they proved that if computational zero knowledge contains a worst case hard problem, so if there exists some non-trivial zero knowledge case, then we can obtain a weaker form of one-wayness called auxiliary input one-way function. Auxiliary input one-way function is a collection of functions indexed by binary strings called auxiliary input. And you may think the length of this auxiliary input is a standard security parameter. So for each security parameter, we have exponentially many functions. Actually, these are candidates for one-way functions. And this has a weaker security requirement such that for every efficient adversary, there exists infinite point on which the adversary cannot invert the function. The point is this infinite set can depend on the adversary. So we cannot fix the one-way function beforehand. And this is the main difference to the standard one-way function. And they also prove that if CZK contains an average case hard problems in error-prone setting, if you know the meaning, then we can obtain the standard one-way function. To sum up, so the non-trivial zero knowledge requires a weaker form of one-wayness. And in the previous work, the gap between this weaker form of one-wayness and the standard one-way function seems to represent the gap between worst case and average case hardness. Now let's see our result. Our main contribution is to close the gap between this auxiliary input one-way function and one-way function when zero knowledge contains NP. One of the main theorem is easily stated. One-way function exists if and only if NP is contained in CZK and NP has worst case problem in IO sense. And this means that the hardness holds for all large enough instance sizes. Namely, we have a worst case characterization for one-way function based only on well-studied notion. And we can also show that if NP admits zero knowledge, then we can exclude heuristic and pestilent simultaneous. And actually, this theorem falls for other zero knowledge classes, SZK and CZKA. So they are actually equivalent. And I want to emphasize that our work actually does not improve the previous work because we need additional assumption that NP is contained in CZK. So I think the correct interpretation, takeaway message from this theorem is the following. For zero knowledge to have a sufficiently rich structure, one-way function is required instead of the weaker form of one-wayness. Then the natural question is how rich structure yields the standard one-way function. One answer comes from meta complexity. This is a paraphrase of our main theorem. And we have the third item here. The problem gap MCSP is contained in the zero knowledge graph, and the zero knowledge graph contains worst case hard problem. And gap MCSP is a problem that asks circuit complexity for a given truth table. Particularly, the task is to distinguish between these two cases, and this epsilon is arbitrarily constant, fixed beforehand. Particularly, the implication from the item 3 to 2 can be very interesting because let's consider the non-trivial zero knowledge. And in this case, whether the whole NP class is contained in the zero knowledge class is completely determined by whether the specific problem gap MCSP is contained in the zero knowledge graphs. And currently, the NP hardness of gap MCSP is a notorious open problem in meta complexity community. But this theorem showed that gap MCSP performs like NP complete when we consider zero knowledge class. This can be an interesting phenomenon for zero knowledge and meta complexity. And this clarifies the difference between our work and the previous work by Ostrowski and Wigderson. Actually, these are incomparable to each other. The previous work by Ostrowski and Wigderson assumes just non-trivial zero knowledge and yields the weaker auxiliary input one-way function. In our work, we considered additional structure on zero knowledge. Some meta complexity problem is contained in zero knowledge. Then we can boost the result and we obtain the standard one-way function. Next, we continue the study. So in the first main theorem, we show that non-trivial zero knowledge for NP yields one-way function. And the next question we ask is, how about the case where the leakage knowledge is not zero? So there is some leakage of knowledge, but what happens if the leakage is very tiny, but not zero? And this situation is captured by introducing knowledge complexity. Particularly in this work, we consider computational knowledge complexity for the honest verifier. Let's say an interactive proof has computational knowledge complexity K if there exists an efficient simulator. And the requirement is this simulator can computationally simulate the verifier's view if it is given additional k-bit knowledge, k-bit string, which depends on the instance and randomness. And this function, knowledge function, can be not efficiently computable in general. So this is a very natural generalization of zero knowledge case. And the dependence on the simulator's randomness is very natural because the leakage of knowledge can depend on the verifier's randomness in general. And we further studied the hierarchy on this computation knowledge, particularly for NP. So there are two extremes. The first one is sufficiently large polynomial, and this is a trivial case. In this case, the prover can send the whole NP witness to the verifier. And the previous theorem showed that if the computational knowledge is zero, then the non-triviality yields one-way function. And we can also show that if the leakage is logarithmic, then we can also obtain the same conclusion. And this means that we can erase logarithmic leakage of computational knowledge. Because if it is trivial, then it is also zero knowledge. And if it is non-trivial, then we can obtain one-way function and we can construct zero knowledge proof for every NP statement. And I think this opens an interesting avenue of research. Particularly if we assume some weaker notion than one-way function. And if the assumption yields, let's say, logarithmic computational knowledge, then we can show the equivalence between the weaker notion and one-way function. Unfortunately, we could not show such a strong result, but we can show something. If there exists an auxiliary input one-way function, then we can save the computational knowledge for every arbitrarily small polynomial. And if it is exponentially secure, we can save the knowledge complexity to arbitrary superlogarithmic function. And these are our main theorems. And now I would like to present the comparison with the recent attempt to capture one-way function by worst-case hardness. So this is actually a very challenging task because one-way function has average case hardness for inverting. And the goal is to capture this notion by using some worst-case hardness notion. And in meta-complexity community, there are two progress on this. The first one is to consider NP hardness of meta-complexity. Particularly, the previous work by Hirahara introduced a new complexity measure called distributional Kolmogorov complexity and introduced approximation problem of this measure, gap MDKP. And he proved that if this problem is NP hard and if NP is worst case hard, then this captures the existence of one-way function. The second type of result is to restrict our attention to shallow computation depth instances. Now, I do not get into the computational depth, but roughly speaking, so the previous work showed that if we consider the worst case hardness of the problem computing Kolmogorov complexity or related notion under the promise that the given instance has small computational depth, then the worst case hardness captured the one-way function. And the first result actually needs to consider new, namely less understood problem, gap MDKP. And in the second result, we need to restrict instances to capture average case hardness by the worst case hardness. Again, our work also yields a new characterization of one-way function by using worst case hardness. In this characterization, we only consider well-studied notions like the NP, CZK, and the standard worst-case hardness, and we do not need to restrict instances. Actually, there is a connection between this work and the first type of work. So let's see implications. Actually, our work yields new insights into the previous Hirahara's proof and simplified it. We observed that actually this assumption yields a well-known notion that NP is contained in SZKA, and by using our work, we can get the one-way function. So we can simplify the Hirahara's proof in one direction. And this clarifies what's happening here. And we can also show that along with the previous work, which studied laconic statistical zero-knowledge argument system, if NP admits laconic SZKA with efficient prover or witness encryption, then we can exclude heuristica, precedent, and minicrypt simultaneously. And this strong conclusion previously was known from the existence of indistinguishability obfuscation, but we can conceptually relax the assumption here. And the same also holds for gap MCSP. So if gap MCSP admits efficient and laconic SZKA or witness encryption, we can construct a public key encryption whose semantic security is based on the worst case hardness of gap MCSP. Now I present the proof overview. First, we consider the following toy case. This is a key part of our main theorem for SZK. SZK is worst case hard, and the gap MCSP is contained in SZK, then there exists a one-way function. Now we show the overview regardless of the correctness of this assumption. First, by the assumption, we can select a specific problem pi which is contained in SZK and it is worst case hard. Then first we use the Ostrowski's work, which shows that for every SZK problem, we can reduce the task of solving this problem in worst case sense to inverting an auxiliary input function. And actually this yields auxiliary input one-way function based on the worst case hardness of this problem. And it is also known that we can reduce the task of inverting any auxiliary input function to solving the problem gap MCSP in errorless average case setting. And the meaning of errorless is Okay, so since this is the average case setting, the algorithm needs to output the correct answer with high probability over the choice of instances. But even if the algorithm cannot solve the problem, the algorithm cannot output the wrong answer. Instead, the algorithm needs to output the special symbol bot, which represents I could not solve the given instance. And we further reduce this task of solving gap MCSP in errorless average case setting to average case inverting a function by using the assumption that gap MCSP is contained in the knowledge class and my previous work. And now we have a one-way function based on this reduction because the original problem pi was worst case half. And in our work, we slightly modify this proof overview for other cases, such as computational general knowledge or computational log knowledge. Particularly for computational general knowledge, or SZK or CZKA, we use the previous work, which yields the SZK one-way function characterization for these classes. And we combine this work with the previous Ostrowski's work, and we can show that for every problem that is contained in, let's say, CZKA, we have a non-black box reduction from solving this problem in worst case setting to inverting auxiliary input function. And we can replace the SZK part in the previous slide with this result. And actually, we can further observe that actually what we needed is a relaxed BBR one-way function property. And by using this relaxation, we can also show the result for computation log knowledge case. For the details, please refer to the proceedings paper. To sum up, in this work, we considered relationships between one-wayness and knowledge complexity in proofs. Actually, we consider the direction from knowledge, low knowledge complexity to one-wayness. And we can show that for the class CZK, SZK, CZK computational log knowledge, the following are equivalent. And there are some open problems. The first is to ask further about hierarchies on computational knowledge complexity. So what if we consider a different notion than auxiliary input one function for example, the existence of hitting set generator or something like that. The second is whether there exists relaxed or related assumption for excluding heuristic and Peschland simultaneously. So any relaxed assumption can be interesting. And the third question is what happens if we consider statistical log knowledge argument system. So it is natural to conjecture that this is also the same member of this theorem. But unfortunately, I personally could not show the result for S log knowledge argument system. This is a specific open problem from our work. And that's all. Thank you for your watching.